Welcome to the Foundry by Forge College. I am honestly so excited for this one. Today, we're diving into an explainer on exactly how Firedancer achieves its blistering throughput by turning theoretical architecture into real-world speed. We're talking about the raw, granular optimization strategies that take a well-designed system and make it absolutely scream. If you've ever wondered how Solana can process thousands of transactions per second while barely breaking a sweat, well, you are in the exact right place.
Okay, let's just quickly run through our roadmap for today. We'll be hitting the need for speed, core optimization tools, the bottleneck whack-a-mole, yes, that's a highly technical term we're going to use, under the hood with the code, and finally, trade-offs and takeaways.
All right, kicking things off with Section 1, the need for speed, upgrading our assembly line.
So, in our previous lesson on scalability enhancements, we essentially built out the distinct lanes of a high-performance assembly line, right? We successfully separated network I/O, transaction parsing, cryptographic verification, and ledger writes. Because we isolated these tasks, slow work in one lane doesn't stall the others. But that raises kind of the ultimate engineering question. How do we actually accelerate the work happening inside those specific lanes? Partitioning was just setting the stage. Now it's time to bring out the heavy machinery.
The difference in architecture here is literally night and day. A sluggish single-threaded queue acts like a massive bottleneck. Everything is sequential, everything is just waiting in line. If one transaction takes a long time to verify, the whole system grinds to a halt. It's like having a single cashier at a packed grocery store, but partitioned independent stages. That allows us to pipeline the work. Because these stages are completely independent, we can now tune the CPU and I/O paths separately for maximum efficiency. Now we've got a fully optimized parallel checkout system.
Moving right along to Section 2, core optimization tools. Let's open up the Engineer's Toolkit.
We have a very specific set of techniques to drop CPU cycles, memory copies, and synchronization overhead. First up, batching. Think of batching exactly like carpooling to avoid traffic. Instead of everyone taking their own car and clogging up the highway with fixed overhead, like system calls and scheduling delays, you group N items into one single work unit. By doing this, you vastly reduce the per-item CPU cycles. Sure, the first person in the carpool has to wait a tiny bit longer for the car to fill up before they leave, which slightly increases initial latency, but the overall throughput of the system absolutely skyrockets.
Next is this magical concept called zero copy. Zero copy is essentially passing around a link to a shared Google Doc instead of painfully printing out physical copies for everyone in the factory. When a packet comes in, we receive it into a pre-allocated buffer pool. Instead of copying those bytes over and over as they move through the pipeline, we just pass buffer references. This dramatically lowers memory bandwidth usage and stops us from thrashing the CPU cache. Memory copies are quite literally the silent killer of performance, and zero copy eliminates them.
Then we have CPU affinity. CPU affinity is basically assigned seating for your factory workers so they don't waste time wandering around the floor. We pin specific threads to specific cores. For example, it keeps the I/O threads pinned right next to the network card. This reduces context switches and keeps the day-to-day need piping hot in the CPU cache. If your threads are constantly migrating between cores, you are losing precious microseconds every single time.
Now, what's really fascinating here is how we can map every single one of these strategies to a concrete, measurable profiling signal. We don't just guess in systems engineering, we measure. Batching shows up as lower per-item CPU time. Zero copy shows up as reduced memcopy calls. CPU affinity means lower thread migrations. We also have kernel bypass, which shifts packet handling into user space. That shows up as massively lower system calls. And crypto offload, where we vectorize signature checks, dropping our overall signature time. This kind of direct, hands-on optimization mapping is exactly what you'd practice in the advanced learning programs at Forge College. You look at the profiling signal, you diagnose the illness, and you prescribe the precise optimization strategy.
Which brings us to Section 3, the bottleneck whack-a-mole, the iterative tuning loop.
We have now arrived at the most frustrating and, honestly, the most hilarious part of systems engineering, the relentless game of bottleneck whack-a-mole. Consider our baseline during a massive market surge. Our flame graphs show that checking cryptographic signatures is absolutely dominating our CPU at 60%. It's choking the whole system. Network I/O and ledger writes are sitting down around 20%, basically twiddling their thumbs, waiting for the crypto verification to finish. This, right here, is our first mole. So, what do? We grab our mallet, and we smack that mole with SIMD-friendly crypto batching and vectorization. We start verifying 32 signatures at once, and boom, signature verification plummets to 15%. A massive success, right?
Well, instantly, network I/O shoots up to 60% and becomes our brand new bottleneck. We fixed the crypto, but all that traffic just rushed forward and slammed right into the network NQ path. The mole has popped up somewhere else.
Naturally, we hit the new network mole. We deploy zero-copy buffer pooling and kernel bypass, slashing those system calls and memory copies. Network I/O drops beautifully down to 15%. Amazing. But wait, this just reveals that ledger writes have now shot up to 60% and are the primary limitation. This is just a perfect demonstration of how optimizations constantly shift the bottleneck downstream. You are never truly done optimizing. You just push the limit to the next part of the pipeline. It's this endless, iterative loop of measure, hypothesize, implement, and measure again.
Let's peek under the hood for Section 4, Code. We'll look at the Rust processing loop mechanics.
Let's actually pull back the curtain and look at how this elegant chaos is orchestrated in the code. We're looking at a simplified Rust-style processing loop here, and it essentially follows 3 steps. First, the network thread writes directly into a pre-allocated buffer. It fetches this from a pool, completely skipping the kernel to user space memory copy. Second, the verifier collects up to 32 items. That's our batching in action. It waits just long enough to fill the batch. And third, it processes that batch using immutable shared references. No bytes are ever needlessly copied. Once verified, the buffers are released right back to the pool. It's essentially a beautiful, continuous, zero-allocation dance.
And finally, Section 5, Tradeoffs and Takeaways. The real cost of aggressive tuning. So, the crucial takeaway here is that while we've built a blazing fast machine, we cannot ignore the real-world operational costs of these aggressive techniques. There is no free lunch in systems architecture, for sure. Every one of these tools introduces heavy trade-offs. Kernel bypass makes debugging network issues a total nightmare and limits your portability across different operating systems. Managing the lifetimes of shared, zero-copy buffers introduces the very real risk of use-after-free bugs, which absolutely threatens the strict deterministic replay required by blockchains. You have to use immutable payload views to stay safe. And finally, because these optimizations interact so deeply, iterative profiling isn't just a suggestion here. It is strictly mandatory. You must profile before and after every single change you make just to see where the bottleneck moved next.
Building a validator like Firedancer is an incredible feat of pushing hardware to its absolute physical limits. To truly master this iterative profiling loop and dive even deeper into advanced validator architecture, head over to forge.college and continue your Web3 education with us. But before you go, ask yourself this: what happens when you push a single node to the absolute edge of physics, but the rest of the global network just can't keep up? That's exactly the chaos we'll tackle in our next explainer. Until then, keep optimizing.